Hi, this is Dr. Jivikas Paul. In this session, we'll discuss about the how to analyze beams, frames, and the truss using strain energy method. A proper cantilever beam of span L. This is a proper cantilever beam. Okay, of span L is subjected to a point load W in the center L by 2 L by 2 as shown in the figure. Analyze the beam by using strain energy method. So here we are discussing about the beams, frames and truss analysis which are of ds value 1. That means these structures are statically indeterminate by 1. Okay, yeah. So first of all we have to calculate degree of static indeterminacy. So degree of static indeterminacy ds equal to total number of reactions and moments minus available equilibrium equations. So how many total number of reactions are there? Generally here fixed support means 3 plus 1 4, but it is not 4 here because there is no horizontal force. As there is no horizontal force, there is no horizontal reaction, so we can neglect this horizontal reaction. So vertical, moment and this reaction 3. And how many number of equations are equilibrium equations are there? 3. But here as there is no horizontal force, so we can neglect sigma fx equal to 0. We have to consider only two equilibrium equations, that is sigma fy equal to 0, moment equal to 0. Okay, so 3 minus 2 equal to 1. So what are the three reactions? Ra, that is Va, Rb or Vb, moment at A, and equilibrium equation sigma fy equal to 0, sigma m equal to 0. Okay, let us now out of these three we need to select one reaction as a redundant. Let us choose Rb as redundant. Okay, so the analysis of this beam for ds value equal to 0, that is for statically determinate structures, so we can analyze simply using the equilibrium equations. For statically indeterminate structures we cannot analyze using equilibrium equations. We need the help of some other equations like compatibility equations. Okay, so that equation we'll get from strain energy equation here. Okay, first of all, after finding ds value that is equal to 1, we have to choose a redundant. Here let us take Rb as redundant. Okay, Rb we have taken as redundant. Now what is the strain energy formula for this one? For bending moment, u equal to 1 by 2 ei integration m square dx. Okay, but here how many spans are there? 2, AC, CB. So we need to take two sections. That's why divide it into two parts. U equal to U1 plus U2. That means UCB, U1 or UCB plus U2 or UAC. Okay, so U1 plus U2. Now what is U1 UCB? 1 by 2 EI integration M1 square dx. So I am taking section here. M1 moment here is M1. Okay, M1 square dx. What is the limits? 0 to L by 2. 0 to L by 2. I am coming from this side. Next, what is this is now what is M1? M1 is nothing but if you consider to the right side, Rb into x. Rb into x whole square. 0 to L by 2. Next. Similarly, we can calculate U2. So U2 equal to UAC equal to 1 by 2 EI integration. Now, here we are taking the section at a distance of x from B. Okay, M2 square dx. What is the limit? L by 2 to L. Okay, yes. Now, what is M2 now? Rb into x minus W into this distance. What is this distance? X minus L by 2. X minus L by 2. Okay, right. Now if we simplify it, we will get this one. Okay, so we know that U equal to U1 plus U2. From Castiglione's second theorem, we know that dou U by dou P equal to Y. This is force, this is deflection. P is force, Y is deflection. Now here dou u by dou RB, redundant we have chosen is RB. So RB, redundant force, equal to, at B the deflection. What is the deflection? YB. But anyhow, as there is reaction here, there is no deflection. That means YB equal to 0. So dou u by dou RB equal to 0. Dou u by dou RB equal to 0. We know that u equal to u1 plus u2. Okay, but we know that u is nothing but 1 by 2a integration 0 to L by 2 m1 square dx. u2 is 1 by 2a integration L by 2 to L m2 square by dx. But if we partially differentiate it, but this is our compatibility equation. So dou u by dou RB, if I do it, dou u by dou RB equal to dou u1 by dou RB plus dou u2 by dou RB, which is equal to 0. Okay, now what is dou u1 by dou RB? 1 by 2a integration 0 to L by 2. Okay, now this one, if I partially differentiate it, it will become m1 2m1 into dou m1 by dou RB, 2m1 into dou m1 by dou RB plus 1 by 2a integration L by 2 to L by 2. If I partially differentiate it, then 2m2 dou m2 by dou RB dx equal to 0. Okay, so if I simplify it, so here 2 will get cancelled. Then if I simplify it, it will become, I will substitute these m1 values which we have already calculated. Okay, m1, what is m1 here? m1 already we have calculated here, m1, and this is m2. m1 is RB into x. m1 is RB into x. Okay, this m1 is RB into x. So these values we have to substitute here. Okay, we need to substitute here. So if we substitute here, we will get this one, m2. Now this is dou m1 by dou RB. If we partially differentiate it, it will become x. Okay, here this value is nothing but x, because everything is constant. Only with respect to RB we need to do. So which is equal to this one. Okay, now simplifying, I am simplifying this, we'll get this. Applying limits, doing integration here, then applying limits here. If we solve it, we will get in this way. So simplify it, we will get in this way. Okay, now RB we have found, RB value we have found. Now we can find RA and MA using equilibrium equations. Apply sigma Fy equal to 0, upward forces equal to downward forces, upward force equal to downward forces. You can find RA. Now to find MA, apply sigma moment about A equal to 0. So this into perpendicular distance, this into perpendicular distance, and MA. So MA is 3WL by 16. Okay. So now you have got this value, and this value. Okay. Now you can draw shear force diagram and bending moment diagram easily. So shear force at CC, CB. We know the process how to calculate shear force values and bending moment values, and in that way we can draw shear force diagram and bending moment diagram. Okay. Now how to find this value? Equate the bending moment equation to 0. Okay, bending moment equation between A to C, equate it to 0. Then you can find x value. Next, let us see how to analyze the frame. Using strain energy method. So this is a frame given. At A and D, there are hinged supports. At E, there is a force. What is that force? 40 kilonewton. Okay, 40 kilonewton, 40. Here also there is a 40 kilonewton per meter UDL on BC, and I value is same for two columns, but for beam it is 2I, moment of inertia, and spans are shown in the figure. Now same, the first step we need to calculate the DS value, that is we have to decide redundant in the portal frame. So degree of static energy, total number of reactions minus equilibrium equations, total number of equilibrium equations. So here 2 and here 2. So 4 minus 3 number of equilibrium equations. So 4 minus 3, 1. So given structure is statically indeterminate by 1. Now we need to, so these are these are free body diagram. VA, VD are the reactions, vertical reactions, HA and HD are horizontal reactions. We need to find these values, these 4 values. First we will find VA and VD using equilibrium equations. To find VD, let us apply sigma moment about A equal to 0. So if I apply sigma moment about A equal to 0, VD into 4, 40 into 4 divided by 2, and this into this. From here we can find VD. Next, to find VA, apply sigma Fy equal to 0. VA plus VD equal to 40 into 4. From here we got VA. Next, apply sigma Fx equal to 0. So right side force equal to left side force. So HA plus HD equal to 40. Now let us choose the redundant here. So I have chosen HA as redundant here. Okay, HA as redundant. Next, in step 2, we need to find the MX equations for each portion. That is for AE, EB, BC and CD. Okay, so here for AE we have to select some section at a distance of x from A. For EB I have selected some section at a distance of x from E. Here between BC I have selected cut a section XX at a distance of x from EB. And see here, observe here carefully, for CD here I have selected a section XX at a distance of x from D, not C here, from D in the reverse order. Okay, right. So we need to calculate MX equations now. For that we have a table. So portions, origin, I, limit, MX equation, dou MX by dou HA. So we have different portions AE, EB, BC, DC, and origin I have taken A here, E here, B here, D here. I values we have written here. For BC it is 2I, limits 0 to 3, 0 to 1, 0 to 4, 0 to 4. Next, MX equation. So here the MX equation, here the MX equation is, what is the MX equation here? HA into X. Okay, this is 0. So HA into X is the MX equation for AE. If I differentiate it, partial differentiation, I will get this one. Now coming to EB, what is the MX equation? Coming to EB, okay, so HA into perpendicular distance and this 40 into perpendicular distance. So HA into perpendicular distance 3 plus x minus 40 into x. So if I partially differentiate it, I will get this one. Okay, similarly for BC also and DC also. See, for BC, if I do, so this into perpendicular distance, this into perpendicular distance, this into perpendicular distance, this into perpendicular distance. And if I take this for this span, simply HD into X. But what is HD? HD equal to 40 minus HA. Okay, so simply HD into X minus HD, because in the reverse order we are going. Therefore, when we go from reverse, generally it is clockwise, but in the reverse order when we are going, minus HT into X we need to take. Okay, and partial derivation is this one. Okay, step 3 is Castiglion's second theorem, applying the theorem. So we know that dou U by dou P equal to Y and dou U by dou HA, because HA is chosen as redundant here, equal to 0. Because at A, as there is a hinge support, there is no deflection at A. Okay, so deflection is 0, so Y is 0. Okay, now, yeah, so dou U by dou HA equal to, now we have how many spans we have here? 4 spans. So dou U1 by dou HA, dou U2 by dou HA, dou U3 by dou HA. So what is U1? General formula 1 by 2A integration m square dx. Then what will it become? Dou U1 by dou HA. So here 2m1 will come, dou m by dou HA. In this way we need to do for U2, U3, U4 also. Okay, now from equation 1, that means from this equation. From this equation. Now what is this one? 1 by 2EI 2m1 dou m by dou HA dx. The same thing I have written here. Okay, but what is m1 for first span AE? That is HA into x. And what is dou m by dou ha? It is x. Okay. Next, for EB span, for EB, this is the span. This is the mx equation. So m2. Suppose if you take as m2, this is the mx equation. We have written here. Similarly, this value dou mx by dou. Next, for different span, 1 by 2a, this value and this value. Similarly, this one and this one. Now, if I simplify this, EI term will go this side and it will become 0. Okay, and now it will become, it is simplified one. And here I have applied the integration. And in this step, the limits are also applied. And finally, if we solve it, we will get HA value as 17.41 kilonewton. And we know that HD plus HA equal to 40, so HD equal to 22.59. So all the relations we have find here. Okay. After getting all the equations, as there is a hinged support, now we need to draw the bending moment diagram. Okay. So at A and D, there are hinged supports, so there is no moments. So MA, MD 0. Now what about ME? Moment at E 17.4 into perpendicular distance. Next, what about moment at B? This into perpendicular distance, this into perpendicular distance. Okay. What about moment at C? This into perpendicular distance, but in reverse order, so minus. Okay. Now we can draw the bending moment diagram in this way. See, at E value is 52.33. Okay, here it is 17.64. At B, so B, and here at C it is a 19.36. At C it is 19.36. So this is a final bending moment diagram. Okay. So in the same way, we can do the other problem also. This is the other problem. Same pressure, same pressure, but this horizontal force is at this point. Here we have only 3 spans in this problem. You can go through this problem. You can practice this problem also. Same procedure. Same procedure. Yeah. So this is the procedure. Yes. So HD value here we have taken HD as redundant. Okay. After getting HD value, HA value is also found, and these are the final shear force diagram and bending moment diagram. Next, we'll see how to analyze the plane truss. How to analyze the plane truss. We'll discuss in the next session. Thank you.